Hello, hello, good afternoon, morning, everyone. It's Mohit from Terex Hosur team, and welcome to the TCCon webinar. People are still joining in. We will wait for another 2-3 minutes, and then we will start.
Hi everyone. People are still joining, so we'll wait for another 2-3 minutes before we start the session. Thank you.
Hello, uh, good afternoon. morning and good evening, everyone. It's Mohit from Terex India team. This we are having our webinar over TC cone crushers. When will be taking us through the webinar? Who is our product manager for all the chambers? This is the webinar is for our 1.5 hour. So approx 1 hour will be our webinar, and then after it will be followed for question and answer. And in meanwhile, if somebody has any question and answers, can write it also. We will take up all the question and answer. Thank you. Over to when we can start the webinar now. Almost a good number of people have joined it.
Hello, everyone. Thank you for joining. As Mohit, let me get on this thing here. As Mohit has introduced me, my name is Wayne VanAntwerpen. I work for Terex, and I've been with Terex since 2003. I've got about 30 years involved in the crushing and screening market. My current job title is the Crusher Technology Product Manager, and basically my responsibilities are around chamber development, technical support, training, etc. for all the Terex aggregate brands. So that'll be the track brands, Powerscreen, Finley, EvoQuip, Magna, and then the broader Cedar Rapids / Terex MPS across the world. The only chambers that I don't really partake in too much with Terex is the VSIs, the Kanika side of things. I do obviously support where I can, but my main focus is primarily around the jaws, cones, and horizontal shaft impactors, and any new technology we're looking to bring through as well. Okay, so the agenda for today is brief introduction to cone crusher styles, different types, the TC cone history, where just very brief, where it stems from, intro to the TC cones and its model ranges, the anatomy of the TC cone, overview of the key features and product benefits. I'm not going to cover the broad spectrum. I've cherry-picked some of the more pertinent ones for us for this webinar. Our automation package that we have for the static units, operational tips to enhance productivity, improve uptime. Again, I've chosen a few that I think that would be easier to adjust and have the most profound effect that you're going to have. Just a basic summary up of key takeaways, Q&A, and the closing. And I do have a real-world case study on making sand with the TC cone. This has been done for decades now, but we're seeing it more and more often these days. So I thought it might be quite good just to put it in at the end to give you an idea, time permitting. Okay, so there are three main types of cone crushers you're going to find in the market. There might be some other variants along the ways, but these are the main ones you're going to find. And a cone crusher is a compressive crusher, so it falls in the line with a jaw crusher. So the first one, which is the focus of today, is the floating bowl cone. So it's the Terex TC cone. The main things to understand the differentiation between the three is how the cone adjusts, changes its CSS, and does tramp relief. So the floating bowl, as per the name, the actual bowl itself, or the upper frame, moves vertically up and down to change the CSS, and it's the same hydraulic system that is utilized for a tramp overload or an overload condition, where it'll allow the top shell upper frame to move up to try and allow any uncrushable to pass through. The screw bolt style cone is like the Terex MVPX cone. Its adjustment is by screwing the bowl in and out, thereby closing or increasing the gap. You use the hydraulic motors to do that through a ring gear, but then you have a different separate hydraulic system that holds their whole upper assembly, which is made up of the bowl and an adjustment ring down firmly to the main frame, and that's what gives you your hydraulic release, not hydraulic release, but your tramp overload control. And then the last one on the list is the floating shaft cut. So the Terex TG and TGS, there's two different styles of the same model. Internally here, this is where you'll see the top and bottom shell are rigidly fixed together through bolts, and internally the main shaft and the head move up and down vertically via a piston at the bottom, thereby changing the closed side setting. And also the same hydraulic system, same piston down at the bottom is used for a tramp overload condition. And as I mentioned, there are two different versions. Your standard version that you'll find, you can run it in secondary, tertiaries, etc. And then the secondary version, which has got a much larger infeed, that's primarily and only used for secondary situations. Excuse me. So here's the evolution of the TC cone, where it all started out. The main thing was the cone comes from the Pexon line. Pexon is no longer, it was absorbed into the Powerscreen brand. But it all started more than 60, 70 years ago with Pexon and Telsmith doing the gyrosphere. You see the old style over here. Similar to that, what you would have probably recognized from a Simon's style cone. The big difference here is it had roller bearings, roller thrust bearings, parallel thrust bearings between the cone head eccentric and the main frame. It was still screw adjust with spring clusters on the outside, no hydraulics there to accommodate any overload condition. And I've labeled it as a hybrid. The reason for that is the head and shaft comes down into the deep eccentric, and there was a bushing there, although in these areas here were roller bearings. Then Pexon eventually went on and created their own autocone, the Mark I, with the roller bearing design as well. But now they converted from the screw style to a floating bowl type arrangement. But that was a two-piece upper frame. You can give an idea. This is the upper frame, and it was two-piece. It was bolted together. Then they moved on. They upgraded that design to a Pexon Autocone Mark II. This is around the mid-80s. It's when they introduced no longer the parallel thrust bearings to a tapered thrust bearing. Still floating bowl style as you see it here, but the two-piece arrangement. Then it moved on to the Pexon Automax, also again the tapered thrust roller bearing design. In 1997, they introduced the 1000 Automax, and in about 2001 was the 1300 Automax. The previous Autocones, you had a 700, a 900, and a 1200. So they evolved into the 1000 and the 1300 as the main lines, especially in the 90s or since the 90s. The most common globally exposure of this style cone was on tracks. So obviously Pexon coming out with their track Automax, and then that was then taken on with Powerscreen and the Finley brands from a track point of view. This Automax style cone TC is the #1 leading tracked mobile cone in the world. It holds a very big market share. So moving on, Pexon Automax, still the tapered thrust roller bearings, hydraulic adjust, again, moving the upper frame up and down, but it's a one-piece. As you can see, we've gone from a two-piece to a one-piece. And utilizing the one-piece expanding wedge ring with hydraulic jumpy jacks. That comes up on the following slides when I'm showing you key features. Then when the Pexon factory and brand was dissolved and brought into the Powerscreen and Finley lines, we went on with the Terex TC cone. The first really leader of the TC cone line from the Automax upgrade was to the TC 1150, launched back in about 2014. This one brought in the line of a higher speed cone with larger throws compared to the previous Pexon Automaxes. And now we've evolved again further on to our latest developments is the TCX line, where we currently have the 1300X, which was launched back in 2023, which is a large throw, high speed, optimized kinematics for that style of cone, bringing out two different eccentric throws. And we have the smaller TC 1000X launching out in 2026 as well. Again, Pexon, if you recall from the 90s and the early 2000s, it was called BL Pexon. How that evolved, you had Brown Lennox back in 1836, and then you had Samuel Pegg and Son, which became obviously Pexon, and they do different markets they were functioning in, which was not the aggregates markets. But as they came down, moved on, Brown Lennox began making crushers in 1930. So Pexon moved to their premises, the current premises that we still have today, where we build most of our crushers is in Colville. In 1990 and 1996, Powerscreen purchased both Brown Lennox and Pexon. And then they merged the two companies, BL Pexon, based primarily in Colville. And then in 1999, Terex bought out Pexon. So you can see how the name BL Pexon came about and the history of where they started and how long they've been making crushers. And just give you a little bit of a visual display of, Pexon in the days they were doing mobile equipment, mobile crushers many decades back. It wasn't just the old track ones that came in the 90s and 2000s plus. But from a more of a non-tracked environment, you got the mobile cones, as you can see from the Pexon, in a more bigger multiple crusher. With two crushers on it. I think you can see there's a jaw here, there's a cone there, and a single cone crushing plant. That's a spring cluster, as you can see. I think that would be the older gyrosphere style with a horizontal screen, but it'll give you a good perspective. You can see the size of this plant, and here's the more modern variants where we have a big, especially now in Cedar Rapids in America, you've got the 7x20 horizontal triple shaft feeding into the 1300X. It's the first real mainline 400 horsepower cone that you'll find on wheels, and we have much bigger structures going into the modular section that we'll find globally as well. So just a brief introduction to the TC cone. You can see the roller bearing design as we're going through with the one-piece upper frame, and I will focus a bit in for later on with the wedge ring design, single hydraulic system on the outside, allowing the cone to go up and down, and tramp relief. So this is very basic. You'll see the roller bearings in there. So here's the current range and where we're going in the future as well. We have the TC1000, which will eventually be replaced by the TC1000X. 1000, the nominal 1 meter diameter head. It's the same with the 1000X, but we've upped the power slightly to 250. We've upped the eccentric throw, as you'll see at the bottom. We have a long throw, short throw. There was a long throw, short throw on the 1000, but we've improved the throw and improved the speed as well. The 1000 has two upper frames to accommodate the different liner configurations, where the 1000X only has one. The 1150, which came in the about 2014 in production, 300 horsepower, roughly 1150 diameter head, also with two throws, long and short, and one upper frame. The 1300, 300 horsepower, nominal 1300 diameter, with only one eccentric throw, two upper frames to accommodate the liners. In the 1300X, we've taken the 1300, same head diameter, increased the throw and increased the power up to 400 horsepower. So it has two throw options and the one-piece upper frame. Excuse me. The anatomy, the internals, and what makes up the TC cone, I'm not going to go through everything. This is the TC 1300X. The main difference you're going to see here is the introduction of the optional hydraulic anti-spin that we have going through. So that's the big difference you're going to note. One piece upper frame, fixed in shaft, and here you'll be able to see we have the upper thrust bearing, lower thrust bearing, and we have the radial bearings as well between the cone head and the eccentric, and the eccentric and the shaft. The hydraulic system on the outside, which controls the adjustment as well as tramp relief, and we have the wedge ring on the inside between the main frame and the upper frame, and another smaller hydraulic circuit, which we call dumpy jacks, that control this expanding ring. I think those are the main components we're going to look at for the rest of the webinar. So what are TC cones? What are they primarily, and the primary focus is designed around these 5 pillars. The strength, we can crush across the board, really hard, tough, arduous rocks. The performance is exceptional, especially with the new TC and TCX lines. Versatility, what the cones can do, the different types of feed, the variance in feed, and our options that we have that allow the change up in the performance to suit given applications. Ease of maintenance, very easy machines to work on, easy to do maintenance, strip, do liner changes, etc. And the bottom line, in coupling all of that, encasing all of that, is the reliability. Very reliable cones. You can depend on them going through changing conditions and applications. And as I mentioned, it's important to appreciate the arduous applications that this cone can safely work in. When I say safely, I mean safely in the sense of ensuring reliability and performance. So just breaking it down to the key features we have on the TC cone: superior product quality, market-leading performance, especially on the track plants. That's where it's most dominant, but there's been a lot of good inroads over the last 15 odd years of introducing these cones into the market in static situations and modular and mobile, meaning on wheels. But the tracked platforms have been supremely successful over the last 2-3 decades, as leaving it as the market #1 tracked mobile cone crusher. Highly placed secondary, tertiary positions in all the aggregates and mining markets. The hydraulic adjust system, as I mentioned, the one upper frame, gives you a precise, reliable CSS control. It doesn't fluctuate. It holds its space, holds its setting, excuse me, allowing for that superior quality without a fluctuating CSS. You can have consistent output grading and overload protection, giving you an immediate return as well. So you have an overload condition, it'll open up and return back to its original setting. The friction, the low friction roller bearing design, compared to that of what you see in the market when you've got the bronze bushings, the most important thing to note is the efficiency and the effective power utilization that you find with the low friction roller bearings, where bronze bushings do generate a lot more heat. So that's a loss of energy, not only inside the crusher and the power supplied, but then you're going to have to add more energy to keep that oil cool. Higher flow rates of oil, bigger coolers, etc. Versatile liner configurations. What I mean by that, we don't have a very large, broad spectrum of liner configurations for our TC cones, but I think that is a strong point, especially with our standard liner. What you can achieve with that liner is phenomenal, and we'll cover that in the upcoming slides. Gradation output control with the long and the short throw eccentric options, but that's primarily on purchase, so we can look at your application and decide what will suit better for you, either the long throw or the short throw eccentrics. And also your gradation control is also well balanced, because the ability to change the CSS whilst crushing. You don't have to stop the machine. You can make incremental changes, so you'll be able to visually see and tangibly see the change in your output. Consistent in-feed size control. Particular cones, let's say the screw style cone, just by the nature of it, your maximum feed size does decrease at the same CSS for any given liner as the wear continues. So you have to continually screw that bowl down, thereby decreasing your maximum recommended feed size. Normally for a full wear life of a liner, you probably drop about 25% in your maximum feed size, where a TC cone is rather consistent with that maximum feed size. So you don't need to be changing up your jaw settings to reduce it to ensure consistent flow through your cone. Consistent performance with low operational costs. You get very good liner utilization, which you don't find a dramatic drop off as your liners are wearing. Again, consistent performance based on consistent feed size without having to change your jaw settings, thereby affecting your in-feed gradation, which will subsequently affect your output gradation. As mentioned right in the beginning, very easily configured for tracked mobile static installations. One of the biggest drivers of this is its installation envelope and operational envelope as well, compared to especially the likes of the floating shaft cone, the TG style, which is much higher. It's easier to get in a track plant where you're very restrained in mobility from a height point of view, especially for transporting it from large structures. When you come into going into modular or fixed installations, you don't have to have a very high structure with longer conveyors because of this operational height that you have with the TC cone. As I mentioned, low maintenance requirements, exceptionally easy and with its serviceability, removing the upper frame to gain access to the concave liner to do a liner change, your mantle, which is on the cone head, which is straight exposed, lifting that off, and the eccentric is very easy, straightforward, all from the top. You don't need large clearances to move those individual items. Low capital expenditure and very long service life with low cost of ownership. Where we come from, that the TC cone is very well structured when it comes to initial purchase pricing, so it's extremely competitive there. And Low cost of ownership, going back to the original points of reliability, you're not going to have frequent failure, especially when you're changing between, if it was an tractor or a mobile platform, where you can be changing feed, changing type of rock, changing application styles. So, your machine will be exposed to varying different criteria of coming in, feed gradings, etc. You don't have to change things up, and you're back to the reliability base point where it's going to work successfully through without warring. You're going to be dropping bearings, etc. And the bearings themselves that we have, our roller bearings, are mostly off-shelf bearings with a very competitive pricing. Look, roller bearings are more expensive than bushings for sure, but one of the general norms that would say, but it just doesn't happen obviously across the board, is it's 3 bushing changes for 1 roller bearing change. So if your pricing of your roller bearings is competitive, and the point definitely a lot more better than some of the other cone crushers out there that utilize roller bearings, and just the fact that the market accepts a 3-to-1 ratio from bushings, you can show that roller bearings are a lot more resilient when it comes into tougher or changing application environments. Okay, so I mentioned earlier on that one of the things we'll be looking at is I think this is a sort of a hidden feature that not everyone sees unless you're doing technical service on it, is the actual the split wedge ring one piece with the dumpy jacks. And what we mean by an expanding wedge ring, this little animation on the side will give you an example. The wedge ring will screw down on threads, sits atop the dumpy jacks, as you'll see here. So we'll screw it down because it's a split ring. When it touches the dumpy jacks, as you'll see in this, we can continue screwing it down, forcing it down. It won't drop in this height, but it'll expand itself on the threads. So it almost acts like a handbrake on a wheel, on a wheel drum. It pushes out, and when you lower the wedge ring onto it, so this point here, when we're screwing it down further, is what we call preload. It then closes the distance between these friction grip pads and the upper frame, and so it's got not a very tight, but a close, snug fit. And then when we energize the dumpy jacks, which I'll show you in an upcoming video, it pushes and expands that wedge ring out even further up the threads, thereby holding the upper frame a lot more stable, allowing it to hold that particular setting over and above with the aid of the cylinders on the outside, precise, and still allows you to make adjustments whilst under load. So if we look over here, touching down, you can bring the liners to touch, and then if we have a closer look at the wedge ring, so that's with it's energized, you can see by the threads, we can de-energize it, making the upper frame easier to remove for service. The other point to note, just looking at this video here, is that the initial point that we showed you, that's how we will also check liner wear. Whilst not crushing, or the cone is static, it's not running, we can lower the upper frame down until you get a touch between your mantle and your concave, and that will go through to our automation package, and we can record your actual wear that you're inducing on those liners, and we can alert you when you're reaching or approaching your wear limit. Let me go to the next slide. I mentioned the low friction roller bearing design. It's just showing you how they go together. You've got your lower thrust sitting on top of the shaft, your 2 radials, and you've got the eccentric that sits above that. And then it too also has a upper thrust roller bearing. You see there for the cone head to sit on, there's a counterweight, and another radial bearing that sits between the eccentric and the cone head. I'm just going over some of the points I've raised previously in the slides. One of the big noticeable differences you're going to see between a roller bearing design and that of a bush style cone is the size of the lubrication tank and the lubrication flow. Giving you a rough example, this TC1300X, we look at around about 30 liters a minute, where you have an equivalent 400 horsepower cone that runs on bushings, could be up to circa 140 to 160 to 180 liters a minute. The reason why you're pumping so much oil into a bush cone is because it's going to generate a lot more heat, and you're trying to dissipate that heat, removing it through out of the crusher back to the tank, going through much larger coolers. So there's a lot more energy involved in pumping the larger flow, a lot more energy involved in cooling that oil. So we have a much smaller oil cooler on this style, much lower flow, and you're not wasting energy because you're losing energy with the bushings through the heat. Okay, next. Please don't tell me you're frozen. I think this is frozen on me. Sorry, folks, I'm going to have to shut this down and restart it. I don't know why it's frozen on me. Just give me a minute. I'd have to just stop sharing for a second. Patricia, just forgive me on this. I'm going to stop sharing for about a minute, and then I'll come back on. Sorry, folks.
No problem.
Yeah, okay. Meanwhile, when restarts, so we will be just for information, we will be having the question and answer session in the end. And in the meanwhile, if somebody has any question, they can put in the chat also. So we will take it up later on. Thank you.
Okay, hopefully you guys can hear me. I'm back again. Got it restarted. The other good, strong feature with this style of cone, as I mentioned, is the liner configurations. We don't have a large array of liner configurations. Our standard liner that we deliver the cone in is what we call a medium coarse. It's just a name associated. If you look at other manufacturers and even some of our other styles of cones, you know, we'll go down extra coarse, coarse, medium coarse, etc. And as you go down in those, the nature of those liners is your maximum feet size will get smaller and smaller. Our medium coarse is, it's a very versatile liner, and as I say, I think it's called a multi-purpose or a jack of all trades, being our standard liner. So the first thing I wanted to show you down here, our medium coarse, and all these cones that we are running, I'm showing on these videos, are running with the medium coarse. So we've got a straight secondary feed you see down here on the bottom left running through our medium coarse. We've got a tertiary feed going in, another medium coarse with great performance and output. And then we have another one here, and this is what I'm sure we've all heard about, all-in feeds. This is actually pushing it to a little bit of an extreme here where there's a lot of sand. This is obviously a sand and gravel application. Just showing you the, again, resilience, and a lot of other cones that we will find in the market. You could not feed a secondary cone with that amount of fines in it. I'll just stress again, that's not really necessary for them to do that, but for this particular site, they didn't have a pre-scalper, and the cone performed safely, reliably, and still at a very good performance level. Looking at the liner configurations we do offer, so we go extra coarse, medium coarse. We have a heavy duty medium coarse, so there are thicker liners. I have it down here. So it's the same profile, just slightly thicker, giving you more wear life. The auto sand, those are the main ones really. There is a fine, but as you can see down at the bottom, you'll only find a fine on 1150, and it's actually more of a replacement between the auto sand and the fine. The bulk of the other machines all have medium coarse. The TC1300, the older design, doesn't have the extra coarse. So there's our liner made up. But as I mentioned, the medium coarse is the jack of all trades, an all-rounder. It can work in secondaries, tertiaries. I've even seen it in quaternaries. And on my case study that I have at the end, making sand, they're utilizing a medium coarse liner. So you're not going to find that type of versatility with one liner on any other style of cone out in the market. The other benefit of having, okay, I wouldn't say much with this because this is filling the voids, but an all-in feed, what is the benefit of an all-in feed? Generally, a lot of OEMs would say you can't have, or you shouldn't have, or they strongly recommend you don't have more than about 10% of material passing through the crusher that's smaller than the CSS it's set at. With adding in material at a respectable level without flooding it like you can see on the one on the right. You allow for more attrition crushing, rock on rock crushing, giving you more superior shape as well. When you start feeding in a very heavily sculpted pre-screened material, your opportunity for a more flaky output product is increased. So putting one of the style of cone, like a TC cone with the medium coarse and a secondary, you don't necessarily need a tertiary down the line to shape up your product. You could get away with it with an all-in feed and on a two-stage plant. Okay, looking at this is more in line with our more modern TCX line, our liner retention systems. So looking at the video that's showing you now is our concave, where we have a tension ring or a locking ring that'll go down. You bring in the concave with the lugs, rotate it, and then we use jacking bolts to lift the ring up and hold the liner under tension. The benefit and the beauty of this is it's you no longer need flame cutting to remove the lugs, to remove the liner. You can drop the tension off the locking plate and just turn the liner out. So that's the principle there. Then on, excuse me, do this one here. This is on the mantle itself and a mantle locking nut. As you can see it down, as you've got a lock ring comes down, similar to the degree to what you find on the concave, where we bring the ring down, bring it back up for some clearance, put the jacking bolts down, and jack it down and hold the liner under compression. The benefit of that, you don't need to cut to burn ring or cut through the manganese to remove the expansion that the mantle will endure during crushing. You can do that with just removing, backing off on the ring. Thereby, no more cutting or welding is required. Far less labor intensive, very easy to do as well, and good for the environment. No more cutting, welding, etc. The automation control we have on our static TC cone, when I say static, I mean non-tracked, is what we call the A6 system. The good benefit of this, we've taken what we already have on the controls we have on our track plants, and we've expanded on that with more additional beneficial controls that we've added in for the stationary, where you can't necessarily get on a track plant. There's good options that we come through. It's very easily navigable. With icons, trying to reduce the amount of languages there, so it's easily understandable from operators out across the field. And you have what do we say? Not bolt on, but you can add in accessories such as level controls that can feed back through the crusher. It's the A6 automation system, where you can adjust levels, and that signal can be sent out to whatever feed control you might have. It could be a belt feeder, it could be a pan feeder, etc. That strongly helps in controlling your level of material and choke feed scenario. I'll expand a little bit more on that when we get to tips on how to improve performance in the field. Okay, so we're looking at tips to improve. Now, this is a very common one that you'll pick up, or people will stress across the board, but I feel it's probably one of the most important ones, is a choke feed scenario. What is choke feeding? It's keeping the material that's being fed to the crusher and the crusher itself filled up past the actual moving parts of the cone head. So you're having a level of material that stays consistently above the inlet to the crushing chamber itself. What's outlined there? Why? Okay, obviously you're getting maximum capacity. You're filling the entire volumetric capacity that the crusher can do. Uniform gradation cubical product. You don't have voids inside the crushing chamber, which you can see on the non-choked or trickle fed scenario. You're not promoting attrition crushing, rock on rock. As mentioned, by not doing that, your shape is not going to be very good. Your output gradation is going to be fluctuating a lot. The choke feeding will give you a much more consistent output grading and a much better cubical product. Your minimum irregular loads, because you've got an even distribution and spread around the crushing chamber, your loading is not irregular. You're not having spike loading, which you can expect to have on scenarios like this, where all the crushing is mostly being done on one side. So as the cone head, which is spinning at roughly anywhere between 5 to 6 revolutions a second, you're going to get very much irregular loading. You'll also get irregular wear, heavy wear, as I mentioned, more uniform wear around the whole liner, and both your mantle and your concave are wearing. If you're feeding predominantly to one side, especially your concave, you're going to have a lot of wear on that side, less on this side. That means when you are running, you could have a CSS set point of say 20, but you have a differential of wear between one side to the other that could be as big as 10 mil plus. I've seen some customers that have a 20 mil, and you think you're running at 20, but you either your CSS is actually getting bigger and back to 20 when you're running, or it could be around, but mostly getting bigger. Very inconsistent output, not the size you need, more recirc, etc., etc. The other thing about choke feeding, there is some academic papers that have been out, you can find on the internet, where studies have been done, is the level of choke feed is also very important. Some people believe that if you just get it above the mantle nut or just above the inlet, that's good choke feed, ultimate. Yes, it's most certainly better than having a trickle or a cavity that isn't full. But they have shown in these studies done on these, as I say, on these academic papers, that the level of choke as you go up improves your gross throughput because you've got a certain amount of weight that's pushing the material through. But don't forget, material passes through a cone via gravity. You will get a power increase though, but you're going to get a much more, you will get a higher throughput with better reduction as well. I've seen this personally with certain of our cones where I've taken it from a low choke, as you can see there, we're getting a certain amount of recirc coming back. It was a closed circuit system. And I took that choke up just a foot, and immediately you could see and hear a difference. And we actually had to end up increasing the feed in rate to the plant because the recirc dropped down dramatically. We had a much better reduction ratio as well. So it's not just choke feeding, it's trying to control the level of choke, but it is a proportional type scenario. You don't want to have 2 meters deep of feed in because you're going to cause problems for yourself. So as you're going up, as I mentioned, what you probably will find as well is your power requirement will go up slightly proportionally as well. So you don't want to go over the point where you start stalling up machines, slowing, stopping, pausing feeds, tramping, etc. So it's not just choke feed, it's the level of choke feed as well. It makes a big difference. In line with the choke feeding, and we got looking at trickle feed, and I'll just expanding on that a bit, but then the other side we have, you could be choke fed, but you're still presenting problems for your crusher. The trickle feed is basically bad feed distribution as well. You're feeding predominantly one side. Sometimes you can fill up a choke as well. You see this quite often, where whether you be feeding from a conveyor or even from a pan for that matter, when it's being introduced to the crusher, it's being introduced on one side. So when you start the crushing process up from an empty scenario, you will get a spike in power requirement, spike in load. You could induce tramp events. You could induce bowl float on screw type cones, and even initial wear. Depends on the paces which you're feeding. Pushing it all to one side is not, it's not best practice. What you want to try and do, whether it's being fed, as I say, from a conveyor or a pan, is when material is introduced, it tries to fall either vertically down to the center of the cone head, or if you can't drop it vertically down, when it's coming in at an angle, it's falling more onto the center or just prior to the cone, the mantle cap. So you're getting a much more equal distribution around it. The other side, and this is from a choked scenario, you think, well, I'm choked, I should be getting the best out of it. You can get bad segregation. The most common causes of bad segregation is if you're in a closed circuit system, and the closed circuit system, you're bringing your main feed coming in from one side and your recirc coming in from another side. So you can see on this is a perfect example. You've got your smaller recirc material one side and your coarser material, your raw feed, to the opposite side. What's that going to do for you? Obviously, your reduction is not going to be consistent. Your wear is not going to be consistent around the concave, because the mantle does obviously rotate, and as it goes into an anti-rotation, but it's primarily your concave that's not going to wear right. Different feed sizes or different size of material being crushed from one side to the other is very similar to having, if you trickle feeding from one side is full, the other side is empty, you're going to get irregular loading. You can start inducing bowl float if it was a screw style cone. Even with a TC cone, depending on the load you're inducing, you could get an imbalance, which could cause bounce, which will eventually give you a tramp. It'll open up the cavity, allow that irregular loading to pass through, and it'll close itself back down to its setting. So and then you can also have it coming off a screen. If you've got two decks feeding that cone, and the one deck's discharging in a particular point and the other deck's coming down, and when they blend in together, you've got the top deck heavies being forced further away, and the bottom, the fines coming off will drop on the one side of the cone. So you see this quite often with belt feeds, where the heavies, because of inertia, get thrown further and the fines drop down to the side. So you can start off with a bad segregation. You're never going to, or you could try and get it as perfect as possible, but it's good to be aware of it. And if you can make an improvement on it, it's best to do it to get the best out of your cone. Cone speed. What I've done here, I mean, this is a whole subject on its own, but I think the good thing about cone speed to just highlight here, there's just some extracts I've taken from some of these academic papers to give you an idea. The main things when you're changing cone speed, generally the manufacturer will give you a nominal speed. If you're going to look to change the speed, you wouldn't want to go more than 10% below or 10% above. Most common thing you would expect to see when you're changing speeds is the faster you go, got more revolutions a second. That means you've got a longer retention time of material in the crusher. That means your gross throughput's going to drop off. If you reduce the speed, it passes through quicker, less impacts, so you'll get more throughput. The problem with also slowing the cone down, because the material's dropping further down per cycle, your power draw would come up. Your reduction ratio drops off when you slow down. Your reduction ratio goes up when you speed her up. These are typical things you can expect. It's never a done deal. And you can actually see it by this particular graph we got here. The other thing you can also expect is if you speed her up, you can expect your wear rates to go up. So there is no one is best. That's why normally OEMs, especially Terex, we will tell you a standard nominal speed, which normally works very well. But if you look to try to push the versatility to try and fine tune it specifically for what you need, speed is a player. Most times guys don't see it or realize it is, but you get a strong benefit of it. And just some of these examples here. This is a gross throughput scenario. See, it's somewhat of a bell curve. So as you're increasing the speed, you will find a point where you get your maximum gross throughput. It doesn't always necessarily mean the slower maximum and it's a straight line going down. No, it's a drifting bell curve to try and find that optimum point for gross throughput. But gross throughput doesn't necessarily mean it's the best thing to go for you. What you're showing you here is you've got different aggregate sizes. So it's just very simple, 0, 2, 2, 4, 4, 8, 8, 16, and plus 16. And you can see as you're changing speed, your net value of those particular aggregates changes. So you could be going down, maybe you wanted to do the maximum amount of, let's say 2.4, and you see it peaks around there, 4.8, it peaks there. It's away from the peak of gross. So you might have to drop off in your gross, but you're increasing the amount of net product you're looking to make, maximizing particular aggregate sizes. That's also the strong benefit of speed. You could do that for yourself. It's similar to a degree to eccentric throw changes. You know, I mentioned we do have a long and a short, but those long and shorts are not changeable and adjustable on site. So one of the easiest things to go with, not easy, but to a degree, is changing the speed. And this example of here, what I like about this graph is showing you gross to net. Here is just showing you another one of product yield going from slow to fast. And this is sort of cherry picked some of the sizes. You can see as you changing your CSS, that'll also vary. That's another player that comes in. And your speed, you can see that it's not a straight line resultant. It does fluctuate. And unfortunately, as an OEM, we can't tell you exactly what's going to happen. This is extremely dependent on the type of rock you're crushing, feed grading into your crusher. But the important thing just to see is the fact that it is not a straight line and it varies. So if you are able to change your CSS and your speed, you can optimize the particular product yield you. Okay, some additional optimization improvements you can do. You know, when you're initially sizing it, get the right liner configurations. That's the beauty, as I mentioned, the TC. It's not a special, you don't need a PhD to try and find out and get the exact right liner, where a medium course practically guarantee you success in just about every situation. Liner metallurgy, I haven't covered that, but that's different type of metallurgy, different manganese levels. Does it have chrome? Does it have inserts like titanium, tungsten to try and give you a longer wear life, improving your uptime? The supplied power, making sure that you're picking the right cone for the power availability you have at your disposal for that particular site. And again, talking about crushing speed. Surge bins are very important, or tunnels for that matter. They strongly assist in maintaining a nice choke on your cone. The biggest problem you have, especially if you're going with a mobile situation or in statics, by not putting surge bins or tunnels between your different stages, is you might get your secondary choked, but the time you get to your tertiary, it's not choked. That's the most important one for you if you're going on the 3 stages, because that's going to control your output gradation that you require and the shape. You know, or you could get it that you can get that choke, but your secondary isn't, knock-on effect. So having some kind of control or some kind of feature in there that you can control and maintain choke feeds is very important. Overflow chutes as well, on surge bins, etc. You can have it that if it fills up too much, you can have an overflow. So you're not trying to back off to avoid spillages. Then you have more recent technologies, okay, which you can have on TC cones or any cone for that matter. But I did mention on the level control, which you can go back through the A6. You can have video cameras too, so you have a visual display. Is my feed rate right? I can see my levels. You can also say you might have a level control. At least you can video. You can make adjustments whilst running without having to climb around the machine. Our A6 coming out this year as well, we will have a telemetry service for it. It will be standard. So we will be able to monitor real-time situations of how our crush is performing, wear rates, power, downtime, alarms, etc. So that will give you access anywhere in the world as to what the machine is performing at. The other also run-of-the-mill good maintenance, preventative maintenance plans for your crusher, where the telemetry likes will help. Having an automation system telling you how much you've worn, you can see how much you worn over a certain time, helps you plan your maintenance better, liner changing. Controlling your feed, as I mentioned to you, controlling the feed, don't have segregated, don't try and go too bony or too much fines going into your crusher. Controlling that max feed size, that's something else that's very important. If you go too big, maybe your jaw, you're crushing your jaw, you've got the right size to your cone, and your jaw plates are wearing and you're not making necessarily adjustments on them to maintain that CSS, the rock gain to your cone is now too big. What that'll endure and cause as a resultant is bridging on the inlet to your cone. The bridging is very similar to that of a jaw. It now restricts the open area of material to come in, and you're going to get a backup. So controlling that maximum feed size is very important. And then the other thing, especially with modern day situations, we're not going back to old school stuff, is keeping your operators properly and trained and up to date with how to operate the machine, how to competently operate it with confidence. That's very important. So key takeaways, what we've gone through today to note about the TC: very robust, reliable, based on its low friction design and the actual overall design that the TC brings to you with the expanding wedge ring, one piece upper frame, hydraulic circuit, on the fly adjustment. Again, that helps you with, again, real-time adjustments to your output gradation, getting your plant balanced. On the fly adjustment makes a huge difference, optimizing your uptime. I mentioned the low friction roller bearing. Versatility when it comes to the design, as I mentioned, with the liners, having that medium course liner, which is your multi-purpose. You don't have to, especially if it's a mobile situation and you're moving from one side to the other, or it could be on the one side and you're changing your feed. You don't necessarily now have to go and waste a liner. Your medium course will work very well. High focus on our maintenance procedures. I spoke about the liners that we have now with our retention systems. No need for welding or burning. And the automation system, okay, coupled with the other features like telemetry, etc., really help you continually run your cone at its optimum. That's the importance of it, and it gives you a lot of live feedback. It gives you feedback at the machine itself, looking at alarms, looking at potential areas where maybe it's not being operated the best that it can. You're picking up more tramp conditions. Maybe the CSS is not right for what you need to do. So that automation system coupled with the other auxiliaries on top of that definitely support. That's me, and I think I've hit the 50-minute mark. Patricia, do you think I have enough time, or should I answer some questions before we just have a quick look at that case study?
When we have one question from Newpunda.
Yep. Okay, let's answer some questions before we dive into that very brief look at a case study. Go ahead. Have you got that question?
Yeah. So, question is regarding the consistent input feed size for TC cones.
Yes.
As the concave wear outs is need to be adjusted for screw cones by lowering the upper frame.
Screwing in the upper frame, yes.
And in floating shaft cone by raising the head assembly.
Yes.
So the feed size should remain constant only if the inlet has a long parallel zone like a primary gyratory, or if the mantle is lower than the concave.
Yeah. Okay. Look, if we look at a screw style cone, most of the time your concave is the highest point on your inlet, or the first point and your mantle nut is much lower. So as you start screwing it down, that actual inlet area where rock can physically pass through begins to decrease. It's not so much the parallel zone that comes into it. It comes also down to the profile of the liner itself. It's hard to explain it without showing images of it. It's not just down to the parallel zone. I mean, you can have, as your liner configurations change, you go from a coarse down to a fine, your parallel zone increases. But yet we can still have a coarse liner with a consistent, or when I say consistent, it's not going to be exactly on the button, but as consistent as possible. You're going to get a small decrease, but on a coarse, the same you'll find on a fine, for that matter. So it's not necessarily the longer the parallel zone, the more consistent the maximum feed size is going to be. That's not necessarily the case. It's down to the overall profile design between the mantle and the concave. But the key thing, if you look at the likes of a floating shaft or a TC style, the mantle nut normally sits level to the inlet or slightly higher. So whereas on a screw, it's a lot lower. Hopefully that answers or covers the point. Any other questions?
Yeah, one more.
Yep.
So does the upper frame of 1300X match the 1300 crusher? Yeah, so question is like if 1300X upper frame is same as 1300?
No. It's a new design. It's a one piece, different liners than what you're going to find on the current 1300. The whole geometry inside is going to be different as well. It's not interchangeable. You can't convert a 1300 to a 1300X by changing the upper frame. Fortunately, no. Any other questions?
Yeah, we have one more question. What is the maximum gap it can open in TC 1300 while tramp relief?
That's okay. I'll explain a difference, because there is no perfect cone style of crushing. A perfect style of cone crusher. Where you have on a screw, style cone, it has the best sort of tramp relief system because, as I mentioned, it's a completely isolated. It has its own hydraulic circuit just for tramp relief, where, say, for argument's sake, a floating bowl or a floating shaft uses the same hydraulics. So a screw style would have a consistent, the same, whether it doesn't matter what liner you have in it, doesn't matter what throw you've got on that cone, and it doesn't matter how much you've worn the liners. It's the same maximum stroke clearance that you're going to have. When it comes to a TC cone, which is very similar to that of a floating shaft cone, your clearance that you're going to have for a tramp will vary consistently. When I say, what I mean by that is you can have one set of liners in it, but if you set the cone to 20 millimeter CSS, its stroke clearance with the brand new liner will be different to if you set it to 40 millimeters CSS. Okay, because that will limit the amount of stroke you have on the adjustment mechanism. And as obviously then, so where I'm coming from is with brand new liners, with a big CSS or the biggest CSS will have the smallest stroke clearance on a TC. But as your liners wear, even at the same CSS, your stroke clearance gets bigger and bigger and bigger. I don't have a number because, as I say, it varies. It varies not only on style, not only on throw, liner, and CSS. So I can't give you a number. But the key thing to note is brand new liners, big CSS on a TC cone will give you the smallest stroke clearance for that particular setup you have. As the liner wear, the stroke clearance gets bigger and bigger proportionally. Any other questions?
No, till now we don't have any other question.
Okay. Well, I'll move on to quickly. I'll just cover this. This case study was done by one of our dealers and distributors out in New Zealand many years back. I'm just trying to think. It's like 2006. There we go. 2006 right there. The key thing I wanted to show you here is that we are utilizing a TC cone with a medium coarse liner. As I say, medium coarse. I don't really like calling it a medium coarse. A lot of times I just call it the standard liner. Making manufactured sand with very small feed. As you can see, here's the raw feed, and they're making a -5 manufactured sand from that particular feed, going through a TC cone with medium coarse liners. The key thing to note here, which not everyone who does this, but I think the conception to do this, I need to make sand, I need to close it down very tight. No, you don't do that. You actually have a larger CSS. You have a CSS bigger than the feed you're putting into it. This particular example, they're 18 millimeter CSS. So what they're doing is choking up the cone. You're getting a lot more grinding going on as well with inside that chamber, allowing for your recirc to come back. So you're initiating a lot of grinding inside there. And you can see, so recirculating load, he's pushing back, probably 50% is coming back. But you can see the product that is coming out of it from the feed that's going into it. So I'll give you an example there. There's your feed with the recirc. So you can see that 50% odd recirc coming back, which is not great from this. After what I've covered you're getting segregation here. You can see the fines on one side and the more raw feed to the opposite side, but that's because of the way and how it's being recirculated. You get an idea of the feed size. It's a mixed size. It's not exactly as they've laid out over here in passing. You can see there's some bigger flakes in it. So that's the feed. Here's your product, giving you an example of the sieve grading of the product they're looking to make. And there you can have a look, see product output percentages, and then the plant that we're using, a Pexon tracked TC1000 cone with its onboard screen and recirculating back. So it's a very brief one, but why I wanted to show this to you guys and share it with you is I think it's a great case study to highlight that versatility that you can utilize with the TC cone. Here I'm making sand. I know the guys are successfully doing this in India, in the market in India, where they're actually going to sites and getting people to no longer utilize actually a VSI. We are using TC cones. In India, they're utilizing the auto sand liner configuration. Guys are successfully doing this in America, where they're recrushing a pea gravel. You see that quite often these days. Guys are talking, you've got a big waste stockpile of a particular size of aggregate that you're not selling, and now you want to reprocess to try and make an aggregate or a product that you can sell. A lot of the time it could be manufactured sand, where guys would generally come in with a VSI or even an HPGR type crusher. You can utilize a TC to do that job and do it successfully. And they are doing it. Unfortunately, we haven't, guys have been doing it for, as I say, some of the guys in America have been doing it for over a decade, and they have a certain way to control it to make sure it works successfully. And with our automation system, we are in the process of looking at and working out new features on it that will help promote and make it easier to do this kind of application, making manufactured sand, running at a CSS that's bigger than the material that's being fed to it. I know you would think it's contradictory to what I'd said to you early on about controlling the amount of undersize, but your biggest killer when you feeding into a crusher with an all-in is the 0 to 5, 0 to 6 feed size. Here they're not feeding that; they're going to feed like a 5 to a 10, a 5 to an 8, a 5 to a 20. So you don't have that fine sand that's filling all the voids, especially if you're trying to grind as well. So it's the introduction of the grinding motion with inside the TC cone, especially with that medium coarse liner configuration, can make you sand as you're seeing over here. Okay, I think that was it. Unless there's any more questions.
Yeah, we have one more question from. So it is regarding S6 that we need more info on S6 control via remote station. We have been told that we can only have a second display within 75 meters from the main control panel. Question is, can we operate the cone from a remote control room around 150 meters away?
Look, the primary reason why there is a stipulated limit to what we can give you a secondary A6 control screen is the communication is via canvas. Canvas, there is a limit, otherwise you're going to start getting interference, bad interference. So that's where the 75 meter comes from. Now I'm not a fundi, or it's not my area of expertise, but I would think you could get boosters, you could get a sort of a junction which would an intermediary. I'm not sure, and don't quote me and say, but Wayne said you can get this. But that is the primary reason why you can't stretch it out too far. Just like Ethernet as well. Ethernet, you could probably safely do it up to about 100 meters. It's a little bit more stable compared to Canvas. But Canvas over a long distance it's limited to that a particular distance. That's the reason why you're being told, no, you can't go to 150 meters. But we can inquire, and I'm sure we can look into, is there any other way we could potentially have a sort of a halfway house, take it 75 meters, do whatever we can to make sure that the signal going from that point to the next point is not corrupted or is lost. But I just don't know. We've never done it to this point. But with modern technologies, there might be something there. But key point is, due to canvas, you're limited to that distance. Any more questions? Right, Patricia?
Yeah, question is, can we retrofit the telematics? Then with, I think with S6 we can retrofit the telematics.
Yes, and I say yes. I'm just trying to think of the back. It just probably depends how far back we're looking. I think because with the telematics, we require a software update on the existing A6 system you have, which is easy. It's a USB. But it depends how far back we go. We would have to review as to how old the unit is. There might be some hardware differences with inside the control panel itself. But we have looked at it, I would say a good couple of years back from now back. Yes, it is retrofittable, and you can buy it through aftermarkets. But when you fit it's the modem, It's the aerial cabling. It plugs in because all our A6 panels are telemetry ready. Even before we launched, well, we've got the telemetry ready for sale. They've always been telemetry ready. So plugging it in, updating the software via USB, and you should be good to go. But it will always be good measure to just check with us first. Is the unit you have, is there no requirement for a hardware update anywhere in it? And the telemetry kits, when they come out with the newer machines, it'll also be, you get a 3-year subscription. I think on the tracked, either Power Screen, Findy, EvaQuip, tracked crushers, I think it's a 7-year prescription.
Yes,
Maybe.
7 years.
Sorry, subscription. Yeah, this one will come out with a 3-year subscription, and then you can, it's part of the price, and then thereafter you can renew. And I see Gary's written down there, it's an 8-month-old TC1000. I would say, as long as it's got an A6 on it, yes, that should be telemetry ready. Any more questions?
Yeah, there is one more question, like to produce like 0 to 3 mm product from 5 to 10 mm feed material. So like one question, if can we produce 0 to 3 mm by feeding 5 to 10 mm in our TC cone crusher? Or like it's more comparison with like HPGR versus TC cone for this application?
Yeah, look, the key thing, feeding it a 5 to 10 and making a sand, manufactured sand. Let's say if I can't remember the exact sizes, if it's 3.5 or 3.7, whatever. Yes, we've done it. Our customers have done it. When you start getting really small to like the 2 mil or sub 3 mil, it's a hard one to call because, you know, feeding or trying to make that product, even though it might be 1.5 mil, it's exponentially different. It's not simple. Okay, so have we done it anywhere? Personally, I'm not aware of. Can it be done? Probably. But I just wouldn't want to give you a strong, confident answer. Oh yeah, no problem, no problem. But we do, and we've done it. And the guys are like in India, I think it's down to about 3.75 minus from a 5 to 10 feed. But generally, if you're talking 5 to 10 feed, if you're going to close the circuit, it's more likely going to be 4 mil to 10 mil. But that's neither here nor there. But going under that point, yeah, it'll be obviously trickier. There might be other things that present themselves or haven't really thought. Where an HPGR, look, an HPGR is a niche product. It's like a VSI. Okay, you can't go and use an HPGR to do what a cone can do with an MC liner. Not going to happen. And an HPGR is designed for crushing those particular small sizes, making sand out of it. That's its niche. That's its specialized area. The TC cone will do it. Will a TC cone outperform an HPGR? It's very hard to say. We're not talking big tonnages here, you know, regardless between an HPGR or a TC. But the key thing is here, you can successfully use the cone to make that, if you so need it, and it could be working in a secondary or tertiary on your site and you want to switch things up, utilize the same crusher to make sand. It's possible. Any more questions?
No, I think that's it. We don't have.
No, okay. Well, thank you everyone for joining this webinar, and I hope it was informative and you took something away from it. If you have any questions, you know, please reach out to the team in Hosur. My email is on the beginning of this presentation, if it'll allow me to get back there. I have no issues at all. You can contact me direct. I'll do my best to help you out, or give you some guidance or some advice. So again, thank you very much.
Yeah, thank you everyone for joining in. Thank you so.
Thank you everyone. Thank you. Have a good day. Bye-bye.